Hi friends, welcome you all. This is Dr. Gajanand Jadhav. Today we are going to study some other topics which are related with the interference. The first topic we are going to study is the interference in plane parallel thin film. Before we study interference in plane parallel thin film, it is very important to know us what is plane parallel thin film. Actually, plane parallel thin film is nothing but a transparent film of uniform thickness which is bounded by two parallel surfaces is known as a plane parallel thin film. A thin film of thickness in the range of 0.5 micrometer to 10 micrometer may be considered as a thin film. A thin film of uniform thickness of the order of one wavelength of visible range, typically of the order of 10 micrometer, which is bounded by two parallel surfaces, that is also called as a plane parallel thin film. For example, a soap bubble, air film enclosed between sheets, glass or mica sheet are the examples of thin films. When a thin film, remember, when a thin film between two transparent medium is illuminated with light, the rays reflected from its upper and lower surface produce interference pattern. Now let us study interference in plane parallel thin film. If you look at this particular diagram, then you will find that we have considered one thin parallel sided transparent film of thickness T. So this is the thin film of thickness T having refractive index N and which is surrounded by air. Now let us consider a ray of monochromatic light, that is AB, is incident on the upper surface at an angle I at the point B. The light undergoes partial reflection in the direction BC. If you look at this, along BC, the partial reflection is taking place, and along BD, partial refraction is taking place. The angle of refraction is here R. At point D, it is again partially reflected along DE and partially refracted along DI. The reflected light DE is partially refracted in the direction EF. Now let us consider to calculate the path difference between the rays, that is BC, and this BDEF. Let EN and BM are the perpendiculars to this BC and DE respectively. Let T is nothing but the thickness of the film, that is BH is nothing but the thickness of the film, to produce ED and BH, to produce this ED and this BH to meet at this particular point G. Then angle, that is HGD, is equal to R. Now the path difference between the two refracted rays can be written as N of BD plus DE minus BN, and it can again be written as N of BD plus DM plus ME minus BN. Let us consider this is an equation number 1. Now we know N is equal to sine I upon sine R. Therefore this can be written as sine I can be written as BN divided by BE divided by sine R is nothing but the ME divided by BE, and this can be written as again Bn minus Me, because this Be and Pe will get cancelled. Or we can write this equation as Bn is equal to N into Me. Now let us consider this is an equation number 2. Now path difference N of BD plus DM plus ME minus N into ME, this can be written as N of BD plus DM. This can be written as BD plus DM, or this again can be written as N of GD plus DM. This can be written as GD plus DM, and we can write it as GM, because this GM is nothing but the GD plus DM. Now let us consider this is an equation number 3. Now in the triangle BGM, if you look at this triangle BGM, then we can write cos R is equal to this GM upon BG. GM upon BG is nothing but the cos R. And we know GM, that is GM, and BG is equal to, we know that is the 2 times that of the thickness of the film. So GM upon 2T, that will be the cos R. Or we can write this equation as GM is equal to 2T into cos R. Let us consider this as an equation number 4. Therefore, path difference is equal to N into GM, and it can be written as 2NT cos R. Now let us consider this as equation number 5. The reflected rays BC suffers a path difference of lambda by 2 on the reflection at point B. Therefore, net path difference between the BC and EF can be written as 2NT cos R minus lambda by 2. Now the film appears bright if this path difference is equal to M into lambda, or 2NT cos R can be written as 2M plus 1 lambda by 2, M is equal to 0, 1, 2, 3. Now let us consider this is an equation number 6. Now the film appears dark if this 2NT cos R minus lambda by 2, that is the path difference, if it is 2M plus 1 into lambda by 2, then that film will appear dark. Or 2NT cos R can be written as M plus 1 into lambda, where M is an integer, therefore M plus 1 is also an integer. Or here at last we can write that 2NT cos R is equal to M into lambda, whereas M is equal to 0, 1, 2, 3, 4, etc. So this is how the interference takes place in the plane parallel thin film. Now, what are the conditions for maxima, that is brightness, which we are getting here? Maxima occur when the optical path difference is M into lambda. If the difference in the optical between the two rays is equal to an integral number of full waves, then the rays meet each other in phase. The crest of one wave falls on the crest of other and waves interfere constructively. And thus, when 2 mu t cos R minus lambda by 2, that is path difference, if it is M into lambda, then the reflected ray undergoes constructive interference to produce brightness or maxima at the point they are meeting. Now 2 mu t cos R, if it is equal to M into lambda plus lambda by 2, or 2 mu t cos R is equal to 2M plus 1 into lambda by 2, then this is the condition for brightness. Now let us study what are the conditions. What is the condition for minima, that is darkness. Now minima occur when the optical path difference, we have already studied, when it occurs when the optical path difference is equal to 2M plus 1 into lambda by 2. If the difference in the optical path difference between the rays is equal to an odd integral number of half waves, then the rays meet each other in opposite phase. The crest of one wave falls on the trough of the other and the waves interfere destructively. Thus, when 2 mu t cos R minus lambda by 2, if it is 2M plus 1 into lambda by 2, the reflected rays undergo destructive interference to produce the darkness. Equation 3 may be written as, that is 2 mu t cos R is equal to M plus 1 into lambda by 2. This considered as equation number 4. The phase relationship of the interfering waves does not change if one full wave is added to or subtracted from any of the interfering waves. Therefore, M plus 1 into lambda can as well as be replaced by M into lambda for simplicity. And thus the condition for darkness becomes 2 mu t cos R into M into lambda. Now interference in film due to transmitted light. Now let us consider here a thin film of thickness T and refractive index N. Now let us consider AB is the monochromatic source of light, that is incident ray which is falling at a point B on the upper surface at an angle I. Here also it is partly refracted along BD. The angle of refraction is R. This angle of refraction is R. At point D, it is again partially reflected along DE and partially reflected along DI. Partially refracted along DI. Produce FE and DH. It produces FE and DH at this particular point Z. There is no phase change due to reflection at point D and at point E, both of which are at a rarer medium, because both are at a rarer medium. Now therefore, consider the path difference between the two transmitted rays, that is Di and Fk, can be written as this Di and this particular Fk can be written as N of DE plus EF minus Dn, or this can be written as N of DE plus EM plus MF, because this EM plus, it becomes EM plus MF, or minus this Dn, or we know that N is equal to what? Sin I upon sin I. Now let us find out what is sin I. Sin I is nothing but the Dn upon Df. This is sin I. And what is sin R? It is MF upon DF. That is nothing but the sin R. So we can write it as Dn upon MF, because DF will get cancelled, or Dn can be written as N into MF. Now the path difference is equal to N of DE plus EM plus MF minus N into MF. It can be written as N of DE plus EM, because EM and plus MF, ultimately here this minus MF will get cancelled, and therefore path difference can be written as N into GM. Now in the triangle DGM, if you look at this triangle DGM, GM upon 2T is equal to cos R, or GM can be written as 2T cos R. Therefore, the path difference is equal to N into GM, and that can be written as 2NT cos R. Now let us consider this as an equation number 1. The film appears bright if 2NT cos R is equal to M into lambda. Now let us consider this is an equation number 2. When M is equal to 0, 1, 2, 3, etc. Now the film will appear dark if the path difference is equal to 2M plus 1 into lambda by 2, where M is equal to 0, 1, 2, 3, etc. The conditions for transmitted light are just opposite to those for the reflected system. Now, therefore, it is seen that the conditions for brightness and darkness are exactly opposite for transmitted and reflected rays. That means the reflection which we have studied in the transparent thin film and the reflection just we have studied in the transmitted thin film are opposite to each other. They are exactly opposite. It means the band seen is bright due to reflected rays that appear dark due to the transmitted rays, and vice versa. Hence, these two systems are said to be complementary. These two systems are said to be complementary. Those two systems, that is a reflection in a transparent thin film and transmission in the transparent thin film. These are said to be complementary to each other. So this is all about this. Thank you so much everyone.